Welcome to this lecture. My name is Mariska Rontetap. I work as a senior process technologist in the urban water cycle for the Delftland Water Authority in the Netherlands. Delftland is one of the partners of the Promises project, under which flag we have developed this course. To the question, where do we find PFAS, the answer is easy: everywhere. In current industrial society, where everything is designed around consumer ease and practicality, PFAS come in very handy in a wide variety of products due to its high stability, hydrophobicity, and oil resistance, from clothing to furniture, carpets, pizza boxes, paint, cookware. Their resistance to biological growth and chemical interactions make them very attractive for application to lab and medical equipment. Because of the repellent unreactive nature, PFAS have been applied in everything from semiconductors to firefighting foam, and as a result we find different forms of PFAS literally everywhere on the planet. But what exactly is this PFAS? PFAS is a group name covering a variety of synthetic fluorine-based chemicals. They were discovered in the 1930s. The first forms were produced in a search for better fluids for refrigerators. Due to their resistance, they initially proved to be very effective as liner for uranium-containing tubing. In the 1950s, the first cooking pans were coated with Teflon, a brand name of polymeric PFAS. In the 70s, PFAS was introduced in firefighting foam in military locations. Also, other training locations have used PFAS-containing foams for decades. These foams, AFFS, or aqueous film-forming foams, have spread out to air, soil, and groundwater, which has caused massive pollution still present today. As we inherited this from previous years, we typically refer to this as legacy pollution. PFAS is defined as a chain of C atoms with fluorine attached to the C atoms. As a minimum, one C atom with two fluorine atoms, as indicated here with the orange dashed line. Perfluoroalkyl substances have a fluorine atom on each of the C atoms in the carbon chain. For polyfluoroalkyl substances, not all C binding spots are covered by fluorine. One or more also have a hydrogen atom. With polyfluoroalkyl substances, the internal distribution of the electrons is less stable than in PER. This makes them a little bit more susceptible to breakdown. The head of a PFAS molecule, here indicated by the three optional shapes on the right, is formed by an alkyl group, which can comprise, for example, a carboxylic acid, a sulfonic, or a phosphonic acid. The number of C atoms in the chain is also an important criterion. For PFAS with a carboxylic acid as a head, a chain of up to 7 carbons is considered short chain. With more C atoms than that, we speak of long chain PFAS molecules. For sulfonic acids, the cutoff is already at 5 C atoms. Regarding the properties of PFAS molecules, important to realize is that the tail of the chain is hydrophobic. It prefers to be not in water, but for example in air. You could imagine that when an air bubble passes by, PFAS molecules end up with the tail in those bubbles. And the alkyl heads of the PFAS molecules, they are hydrophilic. They dissolve fine in water. In this picture, we see a PFAS molecule with 6 carbon atoms, and all carbons are covered with fluorine. Other PFAS will have a different chain length, different side atoms, and the head group as well as the extra side branches can vary substantially. The number of different PFAS chemicals that can be produced keeps increasing and is now already in the thousands. The Environmental Protection Agency's database lists close to 15,000 unique PFAS chemical compounds. Making a subdivision is therefore a quite useful experiment. A subdivision in PFAS is often depicted in the form of a so-called family tree, which sounds friendlier than it is. A main division is applied between polymeric and non-polymeric PFAS. The polymeric PFAS, formed through a repetitive chain of smaller PFAS, are said to be less problematic than non-polymeric PFAS. However, for the production of these polymeric PFASs, non-polymeric are still required, which produce an additional non-polymeric waste stream. There is therefore no such thing as harmless PFAS. From this tree, which is by no means a complete but merely a brief overview, we see the abbreviation starting with the letters PF. That helps you identify a chemical as a PFAS. The final A indicates that we are dealing with acids, and the letter before that shows the head group. PFPA stands for perfluorophosphonic acid and PFSA for perfluoric sulfonic acids. Here we also list two very infamous chemicals, PFAS and PFOA. PFOA is very widely applied in household products and forms the base of the polymeric Teflon. PFAS has been around since 1949. That was the key ingredient of a fabric protector and related stain repellents. These two chemicals are to date found literally everywhere. In the overview, you can see to which category they belong in the PFAS family. Now, we now know how the different chemicals within PFAS are classified, but why do we worry so much about PFAS? PFAS are of that much concern because due to this very hard to break bond between the C and the F atoms, they are very hard for any environmental technology and organism to break down. Any PFAS ingested in our systems via air, through drinking water, through foods, that have been in contact with PFAS containing food packaging materials, or where PFAS has been a part of the pesticides used to grow the food ingested, they can all cause health problems. Specific health-associated issues are still being researched, but what we know for now is that PFAS is related to at least increased cholesterol levels, lower antibody responses, damage in liver and thyroid, pregnancy-induced hypertension, kidney and testicular cancer, among others. It is therefore essential that exposure to PFAS is minimized. That can be done by banning out PFAS from all non-essential uses and being very strict with that, by consciously decide what we buy, what we eat, and by reducing the exposure to PFAS in our environment. Now, with this information, we can conclude with our take-home messages. We have seen that there are very many individual PFAS chemicals. What they have in common is a very hard to break bond between at least one carbon atom and two fluorine atoms. PFAS chemicals are divided along their chemical characteristics, where their C chain length, their type of head group, and the degree of polymerization all play a role. And finally, we have seen that PFAS are related to a number of health effects due to its interaction with specific cells in the human body. And with that, I'd like to thank you for your attention.